All right, this is Geometry A, Unit 4, Lesson 10. We're looking at comparing rigid transformations. So let me distinguish between rigid transformations and non-rigid. Rigid transformations are transformations in which the size and the shape of the object or the preimage is preserved. So all the side lengths are the same, all the angles are the same. A dilation is not a rigid transformation. It's known as an elastic transformation. A dilation is a grow or a shrink. And it does not preserve length, but it preserves angle measure. And so I want to keep that distinction in mind. We're going to look at a couple of compound transformations and analyze them. I'm going to do what's known as a double reflection. I'm going to take this preimage, ABC. I'm going to reflect it across the y-axis. Then I'm going to reflect it across the line y equals 9. So let's go ahead and do that. And I'm just going to do it visually. C is 1 to the left, so C prime is 1 to the right. A is 2, 4, 6, 8 to the left, so A prime is 2, 4, 6, 8 to the right. B is 2, 4, 6, 7 to the left, so B prime is 2, 4, 6, 7 to the right. Okay. And here we go. Draw our triangle. And we can definitely notice the butterfly look to it, the symmetry that pops out when you do a reflection, known as line symmetry with a line of reflection of the y-axis. Okay, now I'm going to graph the line x equals 9, or yeah, x equals 9. To graph x equals 9, find 9 on the x-axis, 2, 4, 6, 8, 9. And draw a vertical line right there. Draw a vertical line. Okay, at x equals 9. And then I'm going to reflect the blue triangle across that. Let's go ahead and do that. Do it visually here. A prime is 1 to the left, so A double prime is 1 to the right. V prime is 2 to the left, so V double prime is 2 to the right. C double prime is 2, 4, 6, 8 to the left, so C double prime is 2, 4, 6, 8 to the right. C double prime. And let's go ahead and draw our triangle here. Now the fun comes when we look at the original triangle and the final triangle, the image, after the double reflection. And first thing I want you to notice is that we did a pair of rigid transformations. So the resulting triangle is the same shape and size. All the side lengths are the same. All the angles are the same. Okay? But if you look at it, you can tell that the orange triangle has been moved over to the yellow triangle. It's been slid, it's been translated. So a double reflection equals a translation. Okay? Not only that, I want to count how far the points moved. Let's count between A and A double prime. So 2, 4, 6, 8, 10, 12, 14, 16, 18. So it translated right 18. Okay? But look at how far apart the lines are. They are 9 apart. So the double reflection is a translation by 2 times the distance between the lines of reflection. Okay? And that makes some sense if you think about it. Almost think of it like paper folding. If you fold the orange onto the blue and then form the blue onto the yellow, we have gone twice the distance between the lines in translating. So a double reflection over parallel lines, a double reflection over parallel lines, is equal to a translation twice the distance between the lines. All right, now I want to look at another compound transformation, and that is a double reflection over perpendicular lines. So I'm going to reflect over the y-axis, then I'm going to reflect over the x-axis. So let's reflect over the y-axis here. So y-axis reflection, 1 to the right, C prime. 2, 4, 6, 7 to the left, so 2, 4, 6, 7 to the right, B prime. A prime, 2, 4, 6, 8 to the left, so 2, 4, 6, 8 to the right, A prime. Okay. And here we go. All right, I get that butterfly effect again. And now I'm going to reflect across the x-axis, which is a vertical reflection. So let's reflect across the x-axis here. C is 3 above, so C prime is 3 above, so C double prime is 3 below. A prime is 2, 4, 6, 7 above, so A double prime is 2, 4, 6, 7 below. B prime is 2 above, so B double prime is 2 below. Okay, and we've got the final image. Again, we conducted reflections, which are rigid transformations, so the resulting image is congruent to the original. That is, it has angles that are the same and side lengths that are the same. But you may notice it's not a translation. It's not just a simple slide, but it's something else. It actually is a rotation, a 180-degree rotation. And so we can also generalize this to double reflections across any intersecting lines. The angle of rotation is always twice, so a double reflection across intersecting lines. I'm going to just generalize this. Intersecting lines equals a rotation of two times the angle of intersection. In this case, the angle of intersection is 90 degrees. And this has been rotated 180 degrees. Okay? So hopefully that makes sense. I'm not going to take the time to do it, but you can imagine the orange triangle, put a pin in the center of the graph and spin it 180 degrees. It's going to end up right where the yellow triangle is. 180-degree rotation. So compound transformations can mimic or behave just like single transformations of other types.